Right. Last week we finished off single crystal. Single crystal diffraction is a technique that gives you every single detail about the molecules in your crystal structure and the arrangement of those molecules in the crystal structure. Sometimes you can't get single crystals, but you can still get valuable information from X-ray diffraction. And one of the instruments we have in this department is our X-ray powder diffractometers. We've got 4 single crystal instruments, but we've also got 3 powder diffraction. So it is a technique that's used a lot by material scientists and solid state chemists. So for a single crystal, as you saw, we had spots on the screen. And what happens when you grind those single crystals into a powder is that the spots will be transformed into a smear. In fact, each spot will be turned into a circle on the screen. I've got an illustration of that here now. So what that means is that the powder instrument is theoretically a lot simpler instrument. For a single crystal, you need to be able to move a crystal so that the Bragg planes come into diffraction position. And that's the same motion that you'd need if you wanted to move a mirror to cause a reflection from that light. Okay, so you have to move the whole crystal in a very precise manner. For a powder, it's equivalent to smashing that crystal to smithereens. So you rely that one little bit of it will be glitching at every position. Okay, so what you're hoping is that by going from a single crystal, which you need to be able to manipulate in order to scatter and reflect the light, to a myriad of little crystals where all crystal planes will be represented in some plane. And when that happens, the determining factor whether you see a reflection or not will be purely that whether it actually is a Bragg in the Bragg position. So the peaks you see will correspond to Bragg diffraction. So the image you see there is actually one I've taken on the single crystal instrument. So that is what you don't want to see on a single crystal instrument. Each of those nice dots I had previously for a reflection has been smeared into a full ring. So what that means is that something, maybe 10,000 spots have all been condensed into that pattern there. So that's one thing. So it's a much faster recording. And the other thing it means is that you don't really need to be able to measure there, and there, because every radial is the same. So you just need to scan from the middle, that's 2 theta of 0, across to the outer reaches to give you the diffraction pattern. So the powder diffraction instrument has an X-ray source and it's got a detector, and what they do is they scan at theta each, which corresponds exactly to Bragg's law. And then each time you get to a position where it's satisfied, i.e. there's lambda is equal to 2d sine theta, you get a peak. And the intensity, of course, will be dependent on the arrangement of atoms in the crystal, and the position will be dependent on the unit cell. That gives you the d spacing. So this pattern here will be unique. Okay, so it's not so easy to abstract structural information from it, but it will be unique and diagnostic for that material. So I'm going to go through now the application. Now, one obvious application is, I've already suggested, is that you can use it for fingerprinting. We can use spectroscopy for fingerprinting as well. So it's a valuable use because it's so simple to do, and you can build up databases of patterns and so on. So this is by far the most common use. So there are other more sophisticated uses, but this is what we would use it mostly. What have I got? What is that powder? Is it what I think it is? And you can come away with that answer in a matter of minutes. Okay, so if the fingerprint matches what you think it will be that material. So as an aid to this, each powder diffractometer we buy comes with what's used to be called the JCPDS database. It's more commonly now known as the powder diffraction file. And what it is it's powder diffraction patterns that have been recorded over many years. by people interested in lots and lots of different areas, whether it's mineralogy or whether it's organic compounds, and they've been reported and stored on the database in the form of d-spacings and the intensities at those d-spacings. So if you think about it, the diffraction pattern will be condensed to a series of numbers, d and the I relative to 100 usually. So of course it can be a very, very big database, but also it can be quick to search as well. So if your pattern matches that, you can then be sure that that is the material. So this is a commercial database. So unlike several of our crystallographic databases, we can't have access to this other than through an instrument. So as I said, we purchase the instrument. It comes with a database which has cost several £1,000s, and this integrated software on the instrument will search for that. So, but it's a very straightforward thing to do. You'll put your material on the diffractometer, press the button, get the scan, and then press the button to get it to compare your pattern with the database, and hopefully come up with a match. So it's a database of intensity versus D. There's an example there. Okay, so the top scan would have been done probably in about 5 minutes. Okay, so we start at 0 2 theta. We wouldn't actually go to 0 because we would damage the detector, but maybe 2 or 3 degrees from 0. And we would scan, typically if we don't know what it is, if we think it's a mineral, up to about 70 degrees, 2 theta. The bottom scale is always 2 theta on these types of instruments because it's effectively the angle between the incoming beam and the outgoing beam. And then at each position where the Bragg plane is present, we get a peak of varying intensity. We then press the button and got it to compare it with a database, and as you can see, it's a very good match for quartz. So the stone I picked up off the beach was in fact, as far as crystallinity was concerned, was mainly quartz, and as you can see, it's a good match in terms of peak intensity as well as peak positions. So I can be very, very confident that certainly the components that diffracting well in my stone is quartz there. So very, very useful and main use for this type of machine. If we want to go more to a more chemical type of application, we could investigate phase changes. Now I should possibly point out that we tend to be, in my area, fairly lax in how we use the term phase. I think probably as sort of physical chemists and so on, you would probably think of phases as liquid, gas and solid, but we tend to use it for any type of sort of crystalline material, for example, which has got a unique composition and structure. But quite often we end up with mixtures, and we end up with one type of crystalline material changing into another one. So we tend to use the term phase rather loosely, and what we mean, any sort of crystalline material which has got a unique structure, I guess. So if we, for example, wanted to look at a compound, a unique compound, tin, we would find there are 2 polymorphs of tin, as there are of things like carbon, diamond and graphite and so on. Now, interestingly with tin, we can convert it from one polymorph to another by cooling. There are other metals you can convert polymorphs by heating them up. They will change the crystal packing. Analytically, they would be the same material. They would still be tin. But you can see that it's very, very, very easy to distinguish here that we've gone from one type of tin to the other because the packing is slightly different. So this is quite an useful technique in metallurgy where the strength of material depends on its structure. And if you made a mistake and managed to crystallize the wrong type of material, for example, in a turboprop blade, it would be disastrous. So this sort of analysis would be used very, very much in, for example, aeronautical type of areas where the strength of material is important, and you've got to make damn sure that you've got the right phase. So very, very easy to distinguish between the 2 polymorphs of tin, as it would be, for example, between different phases of brass, of copper that's been heated and not. Things like cobalt undergo phase changes. So we can distinguish what is ostensibly the same material. We can determine whether it's undergone some sort of phase transition quite easily. Another chemical type use would be to look at chemical reactions. Okay, so the instruments upstairs have actually got integrated sample chambers on them. So it is quite possible to put mixtures of material in there and see what will happen when you heat them. So this is quite a nice example where we started off with magnesium oxide and aluminium oxide. As you can see, they've got quite distinct patterns. They're unique materials, so that there's no mistaking the two materials. Once they've been mixed, that's phase A, and the reaction has started. We can still see the peaks due to magnesium oxide. There's a strong peak there and it's appearing here, and there's some peaks due to aluminium oxide. There's one there and there, but there's also already appearing some extra peaks. Okay, so these aren't present in the original material. If all that had happened when I mixed these materials, they had just remained as a mixture, all we would see would be the two sets of peaks we had here. There'd be a mixture of the two, but in fact we're already getting extra peaks. That is telling us that we're going from magnesium oxide and aluminium oxide to a new phase. And then in this reaction, the mixture is heated over some time, and as you can see, the original peaks are starting to get weaker in B until finally we can see the pattern of the new material, which is a magnesium aluminium oxide. Now, the value of this technique is that we can actually follow the reaction. We can see the original material starting to disappear, and also we can see at which point the original material has completely disappeared. Okay, so in this case we know that we've got a pure phase here, and we don't need to heat any longer, so we could use this as a method of setting up our analytical techniques. Another use, not so heavily used, is we can determine unit cell dimensions, lattice type and crystal system and crystal symmetry. But now this is the sort of thing you would normally associate with single crystal work, but sometimes you're in a position where you can't obtain single crystals, and you might think, well, the type of instruments we've got these days will actually allow us to work with tiny crystals. So you think, well, at least we could grow a tiny crystal. Well, most times we can, but not always. At other times, the reaction that creates the material doesn't lend itself to growing useful single crystals. The method we make it is designed to make that phase, and if we change that method, we would make a different phase, which would be a different material. So we might be constrained to having to heat the material strongly or stir it strongly in order to get the material that we need. But that material won't necessarily have then suitable crystals. So we could sort of start on a path which is sort of parallel to the single crystal method. The only problem is that a single crystal pattern is a myriad of reflections, and each position is a set of angles of a crystal plane. And there is an algorithm that very easily transforms that pattern, the angles of the reflections, into an unit cell. And equivocally, there's no argument, it's clear, as long as it's a single crystal. Unfortunately, by grinding the material, we've lost that angular information. The only information we've got is 2 theta, the 2 theta of Bragg's law. So in order to then reconstitute a unit cell, we have to rely on methods such as trial and error, TRIOR, and so on. So that we can, if the system is relatively simple and the data is relatively good, we could end up with an unit cell, which we can then test against the pattern to see whether it's correct. But it's by no means straightforward. You need high quality data and possibly a lot of patience. But if you can succeed, it does open the door to other measurements later on. So trial and error for a general pattern. If we have a cubic system, the problem reduces considerably. Now, for a general problem, we're looking for A, B and C, and possibly some angles as well, beta for example. Now, if we're working with a cubic system, the problem is reduced enough so that we can actually solve it ourselves, as for example in a problem class or in an examination question. So this is what we'll be practicing in the next workshop. Okay, so for a cube, the 1 over d squared, which is the Bragg d spacing, is equal to h squared plus k squared plus L squared over a squared. Okay, so because the a and b and the c are the same. We could, if we wished, combine this with the Bragg equation. I'll say a little bit more about this for now. If we wanted to, we could actually calculate d spacing for a set of reflections and then use this equation as it is. Okay, so you might have seen techniques where you do that, and that's fine. So we could use this equation as it is. I prefer to, but it's not exclusive, I would prefer to take it to the next stage. And what I do is I replace the 1 over d squared with the sine squared from Bragg's equations. So lambda is equal to 2d sine theta. So all I've got to do is to rearrange this. So 1 over d is equal to 2 sine theta over lambda, square both sides, then eliminate d from the top equation and then rearrange, and I end up with this equation here. So what I've done is all it means is I don't have to calculate d each time. There's no big deal if you're doing that if you want to do it. So sine squared theta is equal to a constant, okay, with the wavelength doesn't change throughout the experiment, times h squared plus k squared plus L squared over 4 a squared. Again, a is a constant for a particular experiment. Okay, for a particular pattern we're working with, that and that is constant. So basically, sine squared theta is equal to a constant times h squared plus k squared plus L squared. And what are h squared plus k squared plus L squared? Remember, we're dealing with the lower part of the pattern quite often. There will be small integers. So h squared plus k squared plus L squared will be things like 0 and 1s and 2s and so on. So these numbers in here, when we've squared them added up, will be also quite small integers. They might be 1s, 2s and 3s themselves. So what we're saying is that sine squared is proportional to a series of small integers. So I think we can probably deal with that now. So the way we deal with it is we say, if we assume that the first reflection, the lowest angle one, is due to reflection 1, 0, 0, then we could then say that for the first theta value, sine squared theta is equal to lambda squared over 4a squared, because h squared plus k squared plus L squared is equal to 1 plus 0 plus 0. So sine squared theta for the first lowest angle reflection, if our assumption is correct, sine squared theta 1 is equal to the constant, if you want, lambda squared over 4a squared. If we're wrong, it's not going to be terrible. So this is the way of doing it. So we know we might be wrong, but the error will become apparent and we can correct. Okay, this is the easiest way of doing that. How could we be wrong? Well, it could be that the system isn't primitive and the first reflection isn't 1, 0, 0. It could, for example, be face-centered and the first reflection then will be 1, 1, 1. So then we would be out by a factor of 3 in that constant there, if you wish. On the other hand, it could be a body-centered system and the first reflection for that will be 1, 1, 0. And if that's the case, we'll be out by a factor of 2. Now this will become apparent as we progress to the next stage. So we're progressing now on the assumption that it's 1, but we know it also might be 2 or 3, the h squared plus k squared plus L squared. So we don't worry about it, it'll become apparent and we'll see it. So what we're going to do is we're going to assume that the first sine squared theta is equal to our constant. So what we're going to do, we're going to divide the first sine squared theta into all the other sine squared theta values. We'll do this in a systematic way. Okay, I'll just move forward a second just to show you. Don't you move. Don't turn all the pages. Don't pages. Okay, this is what I'm going to go back in a second, guys. I just want to sort of point this out to you, that what I'm talking about is a systematic analysis like this. Okay, you'll have your 2 theta values. You could be pedantic, as I have, and then get your theta value. Then you calculate your sine squared theta values. Then you calculate sine squared theta over sine squared theta 1. And if the assumption is correct, we will end up with the columns 1, 2, 3, 4, 5. You can see that column there is exactly that, and I've just rounded it off in the end column. Okay, so that's what I'm talking about, so bear that in mind when I'm talking about that. I'll go back now. Okay, so the h squared plus k squared plus l squared, we tend to call that n because they are just small integers. So the simplest one to detect when we made a mistake is if n are non-integral. So if the column of sine squared theta over sine squared theta 1 isn't 1, 2, 3 and so on, it's 1, 1 and a third, 4 and 2 thirds and so on, that would clearly tell us that the value we used for h squared plus k squared was l squared was wrong, and you would notice that they were thirds and 2 thirds and so on, so you would know instantly that we should really multiply by 3 to get integer values. Okay, so if that's the case, if we don't get integer values, you will notice, hopefully, if your calculations are accurate enough, that they've got thirds and 2 thirds in them, the non-integral part, and you would know instantly to multiply through by 3, and then you would then proceed with the calculation, knowing that the system was f-centered. There is a harder problem to deal with. You couldn't have a completely integral column for both the primitive system and also the body-centered system. Okay, so that's a little bit harder to deal with. So a body-centered cell, what you would find is that as you scan down the column, if it was body-centered now, you would find that there would be one of the sine squared thetas over sine squared theta 1s would be 7. Now, if there's a 7 there, you know straight away that it's body-centered, and you need to multiply the column by 2 to give you the correct n. Why is that? You can't make 7 out of h squared plus k squared plus l squared. You can make everything else. You can make 1 squared plus 0 plus 0, 2, 1 squared plus 1 squared plus 0, 3, 1 squared plus 1 squared plus 1 squared, and so on, but you can't ever make 7. Okay, you can't make 7 from h squared plus k squared plus l squared. If there's a 7 there, the only explanation is that the column should really be 2, 4, 6, 8, 10, 12, 14, etc. And that you've made the mistake, and it should now be multiplied through by 2 to give you those values. So if you see 7 there, but otherwise everything is nice and integral, you multiply through by 2 to give you the correct n, and then carry on with the calculation. Okay, I don't want you to, certainly not in examination conditions, worry too much about this. Okay, I'm putting that there because you can actually convert the n values, once you've corrected them, into h squared plus k squared plus l squared. They will make h squared plus k squared plus l squared, and you will want to do that for certain values. But by the time you've got the corrected column, you will know that the system is primitive, body-centered, or f-centered. You will have the wherewithal to calculate the unit cell dimension as well. So any value on actually determining all the individual h squared plus k squared plus l squared is purely something esoteric. You don't need to do that. Okay, so you can if you wish, but I wouldn't do it, certainly in an examination condition when time is short. Okay, but I'm going through it now just to tie in with previously. Okay, so for f-centered systems, the systematic absences, I don't know if you remember, are h plus k have to be will be absent. Okay, so let's do it as the presences conditions. Okay, so for an f-centered system, the only reflections that will be present will be when h plus k is even, and at the same time h plus l are even, and at the same time k plus l are even. So those will be the only reflections that will be present. And if you look what that means, what it means is that if h, k and l are all even or odd at the same time, that is correct as well. So for example, what it means is that you can have a 1, 1, 1,
that's fine, because 1 plus 1 is even, 1 plus 1 is etc. Or you can have a 1, 1, 3, that's fine, because an odd and an odd makes an even. But you can't have one of them odd or one of them even. They've either got to be all odd, all the HKL is going to be all odd, or they've all got to be even. So that's how that translates. So the first reflection for that will be 1, 1, 1. The systematic absence of the systematic presences, I'm going to say, for body-centred will be that H plus K plus L must be equal to 2, and I must be even for the reflection to be present. So if you're going to see a reflection in a body-centred system, H plus K plus L must be even. And you will see this if you sort of convert your N values into HKL values. Right, I'll take you through that example now. Okay, so we'll practice this next Monday. So bring your calculators. Okay, so generally speaking, the information you need will be, obviously you'll need a wavelength for the instrument. Generally speaking, for copper, for powder diffraction, we tend to use copper radiation, which has got this 1.54 angstrom wavelength. But we have instruments upstairs that have got wavelength of about half that as well. So it's not always that, but usually that for powder diffraction. And the only other information you need are the 2 theta values. We tend to give 2 theta values. If you look in a textbook problem, sometimes you'll see theta values, but the instrument gives you 2 theta values, so I tend to give that as well. And if you're reading it off a powder diffraction pattern as well, there will be 2 theta values. So you need to divide by 2 before putting it into the Bragg equation. So you've got a series of 2 theta values here. Now, there's a very standard way now of dealing with it. Okay, so I should possibly point out at this stage, I tend to phrase this in various ways, given that the system is cubic, is obvious. But quite often I might say, show that the system is cubic. And people tend to worry a little bit about that. But what I'm saying is that if this works, it shows that the system is cubic. Okay, this will only work for a cubic system, and I would be really, really mean to give you a non-cubic system. Okay, so it will be a cubic system, but by working that shows that the system is cubic, and you'll be determining the A value for that system. So this is the method of doing it. There's nothing to stop you, if you wish, to put 1 over d squared instead of sine squared theta. It would work just as well if you use that technique. I will have no problems with that. I'll just give you the method I'm going to use for that. So these are the 2 theta values I've listed on the other page. So make yourself a nice table. I'm not insisting that you divide by 2 as I've done here. I've just gone over the top a little bit. But make sure that you do before you work out the sine squared theta. Very, very important, don't be tempted to reduce the number of decimal places too much. Okay, you need to be on the safe side, 4 significant figures here. Why do you need that? Because you're going to be dividing each of these values by the first sine squared theta. And if you curtail that too much, you'll end up with these having values which are non-integral. Not because they're really non-integral, but because you've rounded off too severely there. So nobody's going to criticize you for having too many decimal places. If you have too few, you could very easily end up with a confusion in that column there. Now, obviously, this is one from a textbook, so everything is absolutely perfect here. The problems I'm going to give you next week, I'm just going to give you some powder patterns, and you're going to actually measure these from the diffraction pattern. So these won't be quite as perfect as that, but you can get meaningful results from that. So what do I get from this? Well, I can see 1, 2, 3, to a very close approximation here. So I know it's not F-centered. There's no thirds or 2/3 there. They're all integer as close as you can get there. So I can then round them off and put them in that column. But what I would do first is I would scan down, and I'm looking for a 7 there. Okay, 7 is skipped. So I now know that this system is primitive, and then I can round off the values here: 1, 2, 3, 4, 5, 6. No 7, 8, 9, 10, 11. And as I said, you don't need to do this. You can put the first 1 or 2 there if you wish. Okay, but this is just to illustrate to you where n comes from. Okay, so that n is 1 squared plus 0 plus 0. That's 2 is 1 squared plus 1 squared, etc., etc. So you can see where the values come from. But for a calculation, there isn't any real value in determining certainly these lower values here. But they are all derived from that. So from that column, I know the system is primitive, and I know, well, I know that the system is primitive, and I know the 2 theta values and so on, and I know the HKL values that goes with that. Now, I don't really need to work out the HKL values because n is equal to h squared plus k squared plus l squared. So I could substitute in the equation to derive the d spacing and hence work out the a value as well. Okay, so I don't need to actually even work out any HKLs if I don't want to. So anyway, effectively what you need to do then is you work out the d spacing using Bragg's law. So the wavelength I've given to you, and I've chosen the first reflection, 2 sine and then 4.91. And that gives me a value of 9.007. That's the d spacing. Now for the first reflection, as we've already surmised from looking for the constant value, the first reflection, 1 over d squared is equal to h squared plus k squared over a squared, but really that's d is equal to a, basically, for the primitive system. So in effect, d is equal to a, so that a is equal to 9.007 here as well. If the system was body-centered, there would be a factor of square root of 2 there. If the system was f-centered, there would be a factor of the square root of 3 there. But again, it all comes out of that equation there. Okay, so we'll be practicing that next week. And if you have a look at past papers, it's the sort of question I ask. So you need to be able to do it. Right. This is another application which is actually becoming more common. We hear a lot about nanotechnology and so on, but how do we know we've made nanomaterials? Nanomaterials aren't different in the sense that they're different crystal packing. It's the same as the material that we could see crystals of. So that fundamentally it's the same. What makes the difference is that the extent of the crystal is very, very limited. So you have different electronic properties and so on. But in terms of most analyses, they are the same as the crystalline material you start off with. So you need a way to know whether you've actually got a nanomaterial or whether you've just got small crystals that haven't gone to the nano dimensions. So I don't know if any of you have seen diffraction gratings, but from diffraction gratings you get very, very, very sharp lines. From, say, double slits, you get quite broad lines. So somewhere between double slits and the diffraction gratings, the lines will become narrower, the diffraction lines will become narrower and narrower until they're as sharp as they are in a grating. And that's exactly true for a crystal as well. Think of a crystal as a diffraction grating for X-rays. And as the crystal becomes smaller and smaller, the perfect repeat we have that goes on almost to infinity as far as the X-rays are concerned now is reduced and reduced and reduced. So instead of getting this very, very sharp, well-defined diffraction pattern, the peaks become broader and broader and broader. So we have a measure now of knowing whether the material is nano or whether it's ordinary. And this is an example here. So if we've got an ordinary material, say the particles are down to a micrometer, we end up with sharp peaks. But as the particles become smaller and smaller and smaller, we would then find, as we were going to the nanoscale, the peaks would get broader and broader and broader. So this is a very, very practical, very, very easy to do method of knowing whether your synthesis method has given you nanoparticles or whether it's allowed the material to crystallize. So this is the opposite of trying to grow good crystals. You're trying to grow poor crystals. But that's just as hard as growing good crystals, and there's quite complicated techniques of trying to make sure that the materials don't clump together to form nice crystals, but stay as individual nanoparticles. So the broadness of the peak is a direct measure of how big the particles are. And the equation that's used to do this is this one here. So I won't ask you to calculate this or anything, but the thickness of the crystal is related to the half width of the peak in the diffraction pattern. Now this is known as the Shearer equation, and it actually uses a standard peak as well. So what it says is that if you've got a highly crystalline material, that the peaks in that material will have a finite width, okay, because the instrument will give you a broadening. So you will have a finite width. So what you do is you subtract that instrument broadening from the actual broadening of your nanoparticle, and you will then be able to measure the thicknesses with this technique. You will find that the peaks for true nanoparticles are so broad that you can actually dispense with this. And you could then end up with that the thickness of the particle is equal to 0.9 lambda, that's the wavelength of the light, over the square of the half width of the peak of your material, times the cosine of the theta value where you measured it at. And that would give you a good approximation to the thickness of the particle. So you would be able to determine whether you were getting to the range you want and whether you were getting pure nanoparticles. Last lot. There are times when you can't get single crystals for whatever reason. And because of the extensive work that's been done on developing the computer programs for single crystal methods, and also on the improvements of the instrumentation, we have now been able to sort of translate that to powder work as well. Now, nobody in their right mind would say, I've got a material here, I want to determine its structure. I know what I'll do a powder method. You wouldn't do that. Okay? There are specialized situations, possibly quite important ones at times, where you are forced to do this type of technique. But basically, you can actually abstract from a powder pattern, given that all the individual reflections are on top of one another and mixed up horribly. You can actually abstract information from that using techniques which have got parallels to the single crystal method. And if you want to compare the two techniques, there are two important differences. I will give you the scheme in a second, okay? But the things I want to highlight is that, remember that a powder pattern has got possibly 100 peaks in it, if you're lucky, and these usually represent thousands and thousands of peaks from a single crystal. So what you must first do, if you hope to try and emulate what you can do in a single crystal, you must try and split those peaks into individual, peaks that are slightly overlapping and overlapping. You've got to try and split those into, or deconvolute them into as many individual reflections as you can. So that's the first thing about the technique which you have to try and do if you're going to have any success at all. The second thing is, which is different to single crystal, is that for single crystal, each reflection spot on the detector can be used as a data point. We don't have to worry about the shape of the reflection. Each one is a full reflection. So we've no worries there. Whereas for powder, everything is on top of another. The peaks, depending on their shape, could have 2 or 3 reflections underneath them. So what's been decided for powder is not to try and work with the deconvoluted pattern, which might be a little bit of a rough and ready method of splitting the pattern anyway, but to work with the full pattern. So what you do in this method is you actually calculate the powder pattern from your crystal data in the same way as you do for single crystal. You calculate the individual reflections, but then you go on then to sort of calculate the powder pattern as well. This is relatively easy to do. The only problem is that in order to get a good match, you need to have a peak shape, a curve fitting shape as well, which adds to their problems. Okay, so you can't just say this is a reflection, that's its intensity. You say this is a reflection, that's the peak shape as well. But so you do end up having to fit profiles and so on. But having said that, sometimes you have no choice. So the two differences are: one, we must, for certain stages, we must deconvolute the pattern as well as we can to get information about individual reflections. And then when we do the least square stage later on, we actually calculate the full pattern in order to be able to estimate how good a comparison we have between the observed as calculated structure. So the black bit
So you might need to put a blue line or something to it on your paper. I haven't got a colour laser printer. But the black bit on the board or on the screen now is what I've already given you. Okay, so the black bit is exactly what I've used for single crystal structure determination. Okay, so that's straight from there. So we start off with cell dimension, space group, and HKL and F list. We solve for the phase problem, Fourier or difference Fourier, graphics editor, least squares, round and round and round, final math, SIF. Okay, so the red bits are the bits I've been talking about now. So if we hope to go down this path here, we have to split the powder pattern into individual HKL and F the best we can. Not easy to do, but it can be done for certain materials. So if we can do that, we can then follow this path. So we can actually try to solve the structure, and we can also construct a Fourier map so we can see where the electron density is and where the atoms are. We can then use the same sort of technique as we use for single crystal to edit the molecule, and then we can go on to the least squares. And the least squares, here's the second difference. We don't try, we haven't got reliable individual reflections now. We haven't, those HKL and F we've got there are quite rough and ready. We've just got to split the pattern the best we can. So really they wouldn't be suitable for least squares. So what we do is we calculate the full pattern from our crystallographic X, Y and Z information, and then hopefully it will match as best you can. And what you do is you effectively subtract the calculated pattern from the observed and use that for your least squares. So if you've got to have any chance of fitting that, you've got this sort of, you've got to try and sort of actually fit the profile of the peaks as well. So you have to squander valuable parameters on peak profile. But if you can do that, you can follow this system. And there are many structures by these days that have been determined using this method of important compounds such as zeolites and novel moths and so on. So this technique has its place, but it's a direct relation of the single crystal. It's actually grown from our single crystal technique, but we've had to add these two extra steps to it. Right, okay, that's all I've got to say about this method. I've come to the workshop next week. Bring your calculators. I would like to have an office hour. I would probably like to have it next Monday and Tuesday, next anyone. So what are your lectures like on Monday and Tuesday? All day, are they?
Yeah.
What about Wednesday?
Free.
You've got a free day on Wednesday, but you don't want to come in on Wednesday.
We've got a gap 1 till 3 on a Tuesday.
1 till 3 on a Tuesday. See, I don't mind having an extended one on a Tuesday. So 1 till 3 would be. Is that common to everybody?
1 till 2 is. I'm not sure about the. I'm not sure who.